Hello everybody. I would like to welcome all of you for today's review session. Actually, our exam is coming very soon. So for this second exam, we are gonna go for chapter 10, chapter 11 and chapter 7. Okay. So today we'll be going through chapter 10. I already posted the worksheet in your Blackboard, also provided you the solution there, but I'll try to do some of that problems here so that you can understand what we are trying to do here. So first of all, you can see here that we are going to talk about the stress transformation. You already did that one in your mechanics of solids class, but here this one will have a little bit adjustment for soil. Okay, so you can see this is a soil element, and you can see here is your sigma y, this is your sigma x, and this is your shear stress here. Usually this type of problem will try to follow the formula that's given in our book, but if you want to follow that book, then basically we have to be very careful about the sign convention. Now I'm gonna show you the sign convention here first, and then we'll just do some of the problem here. Now you can see here that unlike our mechanics of solids class, you will see here that your normal stress, when this one is compression, that would be positive. So here you can see your sigma x is compression, sigma y is compression, so both of them are positive here. So I'll just say like your sigma x 80 and your sigma y is equal to 160. Now I have to find that out. If you see in your figure that this one is asking, first of all let me draw that angle here. So they gave you this angle is 27 here. And this plane is AV plane. Now, when you are going to use our equation, that you must have to measure your angle from the positive x-axis counterclockwise. For example, here, your angle would be actually measured from here to here. Okay, this is your positive x-axis, and then you are measuring counterclockwise to that plane AB. So you can see this is 180 minus 27, so I can say that angle is now if you make any problem, like in this to find out the angle, then basically your whole problem will be wrong. So we have to be very careful about that. Now you can also see what is my tau xy. Tau xy, the convention, sign convention is if the right side upward means like positive. So you can see here the right side is downward. So this one is actually minus 40 kPa. So once I get all these four input, then basically doing the problem is not that difficult. Now let's see the first problem. So the first problem is saying that the maximum principal stress in this element. So we know from equation 10.6 of your book that sigma 1 is equal to sigma y plus sigma x divided by 2 plus sigma y minus sigma x by 2 whole square plus tau xy square. Now if I plug that value here, then basically this one would be 160 plus 80 divided by 2 plus 160 minus 80 divided by 2 which is basically 176.56 kPa. If they ask you to find out the minor stress, principal minor stress, then basically you have to change that one to sigma 3 and this sign will change to negative. Okay? So that's the way you can do like your principal minor principal stress, but they didn't ask that one here, so we are not going to do this. Okay? Then they are asking you, number 2 is, let me clean that board first. So number 2 is basically asking the normal stress at plane AB. So you can see from your equation that sigma at AB, that would be basically sigma y plus sigma x divided by 2 sigma y plus sigma y minus sigma x by 2 cosine twice theta plus tau xy sine twice theta. So if you plug that value here, then basically you will get 160 plus 80 divided by 2 plus 160 minus 80 divided by 2 cosine 2 into 153 plus minus 40 into sine 2 into 153. So basically you get 175.87 kPa. So your answer would be C. Okay? Now if you see the problem number 3, this one is saying that find out the shear stress on plane AB. So for 3, your shear stress at plane AB, that would be equal to sigma y minus sigma x divided by 2 sine twice theta minus tau xy cosine twice theta. So if I plug that value here, then you can see 160 minus 80 divided by 2 sine 2 into 153 minus 40 cosine twice theta means like 2 into 153. So your answer is basically negative 8.8 kPa. So your answer is basically E. Okay? Now let's move forward. For problem number 4 and 5, you can see that our stress in the element has changed. So I'm going to draw that one here. So basically this one is your pole method. Okay? So how to find out the pole? Now let's see the problem they're showing here is so number 4, they are actually give you this figure here, and you have to just show that where is the pole. To find out the pole, basically what you have to do, look at the right side here. Okay, right side here. If you see that what is that value of, like your sigma A, sigma Y, and your tau here. So you can see your sigma here at the right face is 60 and your tau here is equal to 45. And this one is positive because this one is going up in the right direction. Okay? So if I show that one here, like this is your tau and this is your sigma. So basically you can see here that your center is here. So you have to find out the location of this thing, which is 60 kPa and 45 kPa. So you will see this one is actually here at this point. Okay. Now what you have to do, if you take the right side, then you just draw a vertical line of that plane here. So if I draw that plane here, so basically this one intersect with that circle at this point P, and basically this one is your pole. So this point is actually 60, 45. Okay, So one more time, let me explain that one to you. That I'll just take a look at the right side of my element, soil element, and try to see that what is your sigma and tau at this point. So if you see that sigma equal to 60 and tau equal to 45, try to locate that one in the Mohr circle here. Now you have to draw a line which is parallel to this face. So that's actually a vertical line, and this vertical line will intersect with the circle at this point. Actually, in your case, this one is S. So S is basically your pole. Okay. Now, problem number 5, this one is asking the shear stress at AB plane from the pole method. So what you have to do, if you want to find out the stress at any plane, then you just draw a parallel line of that plane from your pole here. Okay, so if you see here, then basically you have to draw a line now which is kind of 30 degree with the horizontal. So if you draw a line here, you actually see something like that. Okay, and if this one intersect here, so that's basically the sigma and tau for this particular plane. So tau AB, sigma AB, and this is your tau AB. So your shear stress at that point is basically, if you see the graph here, then you can just see that one is actually minus 40. Okay, one more time. If you know the location of the pole, pole is basically a unique point. Okay, it doesn't change like if you consider this side or that side. Every time you have to look at the right side and draw your pole. Once you draw your pole, then basically the shear stress or normal stress at any particular plane, you have to draw a parallel line with that particular plane and see that where this one intersect with the circle. Okay, for example, let's say I'm trying to find out the shear stress and normal stress at plane CD. So what I have to do, let's say it's 45 degree. It's not in this problem. Okay, I'm just trying to explain that one to you. So what you have to do, like here is your pole. So you just draw a plane 45 degree with this horizontal. Now you can see this one intersects here. So the coordinate of this point is basically your tau CD and sigma C. So that's a graphical method. You have to read that one from the graph. Okay, there is no calculation here. But this is the advantage of this method is like once you draw your pole, then basically you can find out the normal and shear stress at many different planes. Anyway, so we'll move forward. Let's see the next problem here. So problem number 6. This one is showing you the circular steel water tank will be constructed on a soil that has a unit weight of 128 pound per feet cube. The tank creates a bearing pressure of 6 kSf on the soil below the foundation. Now, The problem is asking the increase in vertical stress at point A after the tank is built. Okay, so if I draw that figure here, let's say this is the center line. So the radius we usually call the uppercase R, which is actually 50 here, okay? And then we are trying to find out a point here which is actually 50 feet below. And the distance from here to here, we call that one lowercase r, which is actually 50 minus 15. So this one is actually 35. And the depth, we call that one z, which is actually 50 feet here. Your r, uppercase r is 50, and your lowercase r is 35 feet. To do this type of problem, actually you will see the figure 10.22. 10.22 in your book, you can just see that what is all those r, small r, lowercase r, and z is. Now you can see here that you need two things here. First of all, your z by r, which is basically 50 divided by 50 equal to 1, and then your r by r, lowercase r by uppercase r, which is 35 by 50. Now you go to the table, which is 10.8 and 10.9. We know that your del sigma z change or increase in your vertical stress is basically Q into A prime plus B prime. Q is the stress coming from the foundation, which is actually 6 KSF here. And A prime and B prime is the function of your Z by R and R by R. Okay? So you can find out this A prime and B prime from the table. So your A prime from the table, actually you will see in the table you don't have any value for R by R 0.7. You have value for 0.6 and 0.8. So for 0.7 we have to just get the average of that. Okay? So your A prime would be 0.24697 plus 0.21468 divided by 2. So for 0.7 that would be, let's say, 0.23. Similarly, if you go to table number 10.9 in your book, then basically you will find out your B prime from there. And again, you have to get the average for 0.6 and 0.8 to get your 0.7 here. So you can see this one would be 0.27819 plus 0.21978, which is actually 0.25. So if you plug those values here, so your del sigma z, actually del sigma z means like increase or change in your vertical stress. That would be 6 and then 0.23 plus 0.25, which is actually 2.9 KSF. So that's the change in your vertical stress. So at a depth of 50 feet, even though you are putting 6 KSF here, but the pressure here will decrease, and this one will be 2.9 at point A. So that's basically the answer is your E, 2.9 KSF. Problem number 7 and 8. This one would be a little bit heavy duty here, but I'll explain that one so that you can understand easily, okay? So So this is 10 feet here, 10 feet here, 20 feet here, 10 feet here, 30 feet, and 20 feet. This is the point A here. Now the question is asking that a L-shaped building will be constructed on a soil that has a unit weight of 110 pounds per feet cube. The building creates a bearing pressure of 8 KSF on the soil below the foundation. Now you have to, the first question it's asking that the vertical stress at a point 20 feet below the point A. Okay, vertical stress before the construction. Okay, before the construction, what is the vertical stress at point A, which is 20 feet below? Okay, so we know that, let's say this is problem number 7. So vertical stress or overburden stress, that's basically gamma H, and your gamma for that soil is given 110. And this one is H is 20 feet, so you can see that's actually (2.2 KSF). That's your answer. Okay, that's just before any construction. Now you are basically construct this building there. This is the plan of the building, and then basically trying to find out what would be the change in stress at point A at a depth of 10 feet below the foundation. Okay, so this is a little bit difficult one, but you already know that you can find out the stress of at any corner of a rectangular slab. Okay, corner of a rectangular slab. That's basically a function of I3. Okay, so we know that for any rectangular section, if this load is coming here is Q, and at any corner, at that corner actually at a certain depth, your del sigma z is equal to Q into I3. Now you can see here this is not a rectangle, it's kind of a L-shaped building. So in that situation, what we have to do, we have to make that slab in such a way that you know the corner of each of the slabs. So here, let's say I can just write from this one. Let's say I'm dividing that one like this. Let's say this is B, this is C, this is D, this is E, F, G, and H here. Now you can see here that the del sigma z at point A, which is 10 feet below the surface, is basically Q I3 of ACDH, this triangle, and you can see this is a corner of that, okay, then plus the I3 of ABFG, which is actually this rectangle, and this is the corner of that one. But you can see one thing here, that when I'm taking this one plus this one, then basically this area is counted twice. So I have to take the impact of one of that thing because I know that this is the corner of this rectangle too. So what I have to do, just I3 ABEH. So that's the formula I'm going to use here. Now for I3, which is actually a function of length, width, as well as the z. So let's try to see for each of that rectangle that what would be my I3. Let's say for I3 ACDH, so your M is basically B by Z, and N is equal to L by Z. So ACDH, you can see L is 30 and your B is 10. L is always bigger than your B, okay? Whatever rectangle you take, the longest side would be your L and the other side would be your B. So here you can see B by Z equal to 10 by 10. 1, and this one is 30 by 10 is equal to 3. So basically if you go to the table 10.10 in your book, then basically you find out your I3 from there, which is actually 0.2034. Similarly, we can find out what would be I3 for this one. Okay, so for I3, ABFG your M equal to B by Z and N equal to L by Z. So your B by Z would be 10 by 10 and L here is 20 by 10 is equal to 2. So you will see your I3 from that same table, 10.10 is 0.1999. Similarly, you can just find out your I3 for this one, ABEH. So you can see ABEH, which is 10 and 10 here. So M equal to 10 by 10, N equal to also 10 by 10. So for M equal to 1 and N equal to 1, your I3 would be 0.1752. So if I plug all those values here, so basically that would be Q equal to 8 KSF, then I3, that's actually 0.2034 plus 0.1999 minus 0.1752. So this one is basically 1.82 KSF. Which is, the answer is actually your E. So basically you have to do a lot for this particular problem, but you will get a little bit more time for that. Okay, but you have to remember one thing all the time, like if you consider like several, like rectangle, every time A has to be the corner of that rectangle, because otherwise you cannot use that I3 thing, because which is applicable only at the corner point for any rectangle. So you can see for this rectangle A is the corner, for this rectangle A is the corner, for this rectangle A is the corner. So that's about it. So today we'll stop it here, and I'll give you another review for chapter 11 in the next day. Thank you so much for your attention. Bye.